Okay. Also, guys, so another warning is you're all on my email list, right? Stay tuned for sudden announcements. There are not going to be announcements that will be about the exam, but something may happen. I'm not sure what will be this Wednesday. I'm not sure what will be this Tuesday. I might need to attend to it, okay? All right, guys. So sorry, 1 second. All right. Thank you, Fnu. All right, guys. So we are coming. We have come to a very interesting point in the subject, and here it is. So I'm sure you noticed by now that when you are describing, when you're trying to calculate probability, you are taking account of the universe, right? When you throw a pair of dice, you notice that the possible universes are the values on those dice that can appear. When you throw even a simple coin, the universes that you consider are universe in which head appears and the universe in which tail appears. And why are those our universes? Is it really correct to eliminate everything else? A coin is not tossed in vacuum, right? The coin exists in a much vaster, bigger universe. So as you throw a coin, people hurry up and down the street. Birds are flying in the sky. Grass is breaking out of the ground without anyone to notice how it's growing. Planets, move around the sun, and galaxies are speeding away from each other. Why am I able to ignore all this information and just focus on a coin? Do I really ignore it? Okay, what information is relevant for the calculation of probability, and what information can be discarded? So let's consider this initial situation, guys. Right? So let's see how a probability is influenced by knowledge of something else that happens. Okay, so you're interested in one event and you know something else happened. How is that going to influence the probability? So the way we ask this question is we're trying to say what's the probability of E given F. Okay, we know that event F occurred and we want to know what's the updated likelihood that E might have also occurred. So to make it precise, let's begin with the experiment in which we flip 2 coins 20 times. You understand? We flip a pair of coins and we do that 20 times. This is an actual experiment that I performed by actually flipping coins 20 times. Good. I just threw a bunch of them at the same time. So let E be the event that coin 1 comes up heads, and let F be the event that at least one coin lands up heads. Good. So that means that what I imagine is that when I perform this experiment, I pay attention to the relative frequency of first coin being heads, given that at least one was heads. Understand? So that means that here, this I can ignore. Tail, I can ignore. Head is one coin was heads, right? I colored them in red, and the occurrence of F, you can calculate here. The occurrence of F is simply 14 outcomes, right? So it happened 14 times that at least one coin was heads. So you can see here it's happening once, twice, 3 times, 4 times, right? Here we have 5 times, 6 times, 7, 8, and onwards. You see, I counted 14 times. And out of those, so out of those 14 situations, I want to know how many did I have where the first coin displayed heads. And I calculate this is the occurrence E intersect F, which I marked as blue and red here. Clear? Blue and red. So E intersect F had 7 occurrences. You understand why I say E intersect F? Because if F occurred, then the only way E can occur is if it's the event E intersect F that occurred, because F already happened, right? So if E occurred, then both E happened and F happened. Clear? So then the relative frequency in this experiment happens to be simply 7/14, which is 1/2. Now, this is not a very good estimate of what will be the general situation, because tossing coins only a few times, right? The number of times that at least one coin was heads is just 14. It's very, very small number. But we imagine that perhaps the relative frequency will be converging to a precise number if I do the experiment again and again and again and again. Yes? And that's what I think is happening when I define this definition, guys. Can you see what I mean here? So probability of E given F, I consider the number of trials where F occurs to go to infinity, and I calculate the number of times EF happens among those trials. Make sense? So my universe is now F. I don't consider situations where F doesn't happen, because I'm only interested in the relative frequency of E within F. And so we want to relate it to the original probability. That's what we're trying to do here. Okay, so you understand that by frequency, we imagine this to be this naive definition of what relative probability is, or conditional probability is. And of course, I switch the limit. Look at it. If NF goes to infinity, that will imply that N goes to infinity, right? Because N is just the number of overall trials that I perform the experiment, and F is the number of trials where the extra condition happened is that F occurred. So then I can take this and multiply by 1 over a numerator and denominator, and I see that in the numerator I get the definition of the general probability of E intersect F, and in the denominator I get the general definition of the probability of F. So making that assumption, you see why you define conditional probability of E given F to be the probability of E intersect F divided by the probability of F. Are you with me, guys? You understand how it's not mathematics, it's a sort of philosophy, nothing more, right? I have a philosophy of what I believe should happen, and I'm trying to express it using those symbols. There is no logic to why there is a convergence here, and you can do it with another technique, but that gives you this idea of why the definition is made this way. Why is it defined to be this conditional probability? Yes, of course, because F intersect E and E intersect F is the same collection of outcomes, right? What is E intersect F? It means that E is a collection of particular desired outcome, and F is a collection of particular desired outcome. E intersection F means that we have outcomes that are common to both of them. Everybody understands? Yes, guys? The probability of E intersect F is probability F intersect E, the same thing. Okay, so this works. This frequency interpretation clearly works when probability of F isn't 0, and we make that the definition of conditional probability. Right? Conditional probability is simply defined to be the formula that we extracted. Let me just write it again, just to be sure. Conditional probability, guys, P E given F is defined to be probability EF, or if you prefer, you can write it as FE divided by probability F. That means if F happens, the relative frequency in which E happens is this formula. And you see that from the running frequency that I tried to explain above. Make sense? You see why that seems to be a good definition. Here is a question, guys. Let's see if you can solve it. If 2 fair dice are rolled, what is the probability that the first die lands on a 3, given that the sum of the dice is 8? Let's see if you can calculate it in one or another way. Very good. Yes, 2 people got it. That's very good. Oh, a lot of people already begin to get it. Amazing. Let's see it. Yeah, so how do we calculate, guys? So we can do it in 2 ways. One way is that we assume that it happened that sum is equal to 8. And there is an extra thing that we notice is that if sum is equal to 8, any 2 outcomes that produce 8 are equally likely. You agree? Because there is no preference to how 8 was produced, because randomness means that it's completely indifferent to anything. So if 8 actually happened to be produced, it's one of those 5 outcomes, and only one of those outcomes makes the desired event where the first die is a 3. So it's 1/5. If we were to use this definition, guys, so the full sample space contains 36 possible nodes, right? 36 number combinations. So probability of E given F is the probability of E and F. Now probability that first die is a 3 and the sum is 8 means the probability of the node 3, 5, which is 1/36. The denominator is just the probability that sum is 8, and that will be 5 outcomes out of 36, which gives us 1/36 over 5/36. Multiply denominator and numerator by 36, and you get 1/5 just the same way. Good? A fair coin is flipped twice. What is the conditional probability that both flips land on heads, given that A, first flip lands on heads, that's A, guys, and B is at least one flip lands on heads? Make sure that you answer it carefully, okay, guys? Think about it and justify. So you understand we threw it twice. First question is, what's the probability that both are heads, given that first was a head and B is at least one was a head? So try to see if you can answer both A and B simultaneously. Write them together when you submit your answers, if you can. And guys, try to use concepts that we just learned, okay? So, I mean, some of you are aware of some other ideas in statistics, but we will get to them. See if you can understand it using just what we did. Okay, good. So far it looks promising. All right, seems very good so far. Anybody else, guys? I don't have everybody answering. This is still an easy question, yes? It's not like a question about a bird laying an egg underground. If I asked you guys, a bird laid an egg underground, what is it? That's a hard question. That's a riddle what I asked you, by the way, but that's another time. All right, good. So I think we had a lot of the same answers. So let's look at it, guys, carefully. So first, A. If I'm claiming that, here is how I do it. I don't use independence. I don't discard information. I haven't talked about those things. I say, okay, we assumed that the first coin was heads, which means I only have 2 possible universes. My universe consists of information about first coin and second coin. It's either head-head or head-tail. And then I say, okay, there is no preference. The coins are fair. There is no preference between the two. Therefore, the probability that both are heads is 1/2. Good? I do that by restricting my universes. If it happened that the first coin is heads, then there are only two possibilities. By the way, guys, notice some of you might have just decided to ignore the information on the first coin and just deal with the second coin. That's not what I did. I deal with both coins together. That's my universe, both coins together. It's just that if the first is heads, second could be tails or heads. So I have two universes, two possible universes, and each of them is equally likely. Therefore, the probability is 1/2. Good. Now for the other situation, I said at least one coin landed on heads, which gives me three possibilities: either head head, or head tail, or tail heads. And only one of those possibilities is giving the desired result, right? Where both are heads. You see, so that's how you get 1/3. You see why before we had 1/2, now we have 1/3. Wonderful. So here we make a certain observation, guys, which we were using indiscriminately, but let's just verify that it's true. And this observation is the following, guys. Suppose that S is a sample space with equally likely outcomes. Then I'm claiming that when you reduce that sample space to a smaller sample space F, in other words, assume that something happened. So some outcome in some collection of some sub collection of S happened in F, right? Then the probability of any specific X that happened within F is equal to any other X that happened within F. Make sense? So this is the situation, guys. So suppose that S has n possible outcomes, each of them are equally likely, and F has m outcomes, each of and then I want to show that each of the outcomes in F will be equally likely if F had occurred. So the probability that X occurs, any X within F, is just according to the definition, the probability of X intersect F divided by probability F. But what's X intersect F? X is a particular event in F, so X intersect F is just X. So this is probability of X divided by probability of F. Now what's the probability of X in the sample space S? It's 1/n. What's the probability of F? It's m divided by n. So you can see that the probability of X is 1/m. Right? Each individual outcome in F is equally likely to have been the outcome that created F. Let's consider this question. Student is taking a 1-hour exam. The probability the student is finished with the exam in less than X hours is X/2 for all X between 0 and 1. Given that the student is still working after 0.75 hours, that's basically 3/4. What is the probability that the full hour will be used? What's the probability the student will not be able to finish before the hour is done? Calculate. Given this information, of course, guys. Let's wait maybe 1 more minute, guys, and we'll do it together, yes? Okay, thank you, Kunyuan. All right, guys, let's work on it together. It's a bit unpleasant, but it's a matter of symbols, guys. So let f sub x be the event that student is finished in less than x hours. Okay, x hours or less, let's to be precise, right? Either at x hours or less than x hours. Okay, and we're told that this probability is x over 2. I know the probability of f of x. Now the probability I'm interested in is that the student is not finished in less than 1 hour, given that he is not finished within within 3/4 of the hour. So what is that? By conditional probability, it's just the probability of this event in the denominator, the probability of the intersection of both events in the numerator. Now here, guys, think about it, right? So one set belongs to another set. So if the person did not finish within an hour, certainly the person did not finish within 75% of the hour. Yes? So the intersection of those two events is probability of F1 complement. Are you clear? I don't even bother. Look at it. F complement of 1 implies the f complement of 0.75, which means f 0.75 is a bigger collection. Do you understand what I mean? It's like, guys, if it rains, then my roof leaks. So my roof leaks, it has more causes. It has rain included, and it might have other things. Maybe my neighbor is spilling water. You see? So it's a bigger collection. And if you intersect two collections, the intersection is the smaller collection, of course, if one is contained in the other. So we have this situation. Now, I can calculate probability of F1 complement as 1 minus probability of F1. In the denominator, similarly, 1 minus probability F of 0.75. So what is that? This is 1 minus 1/2 divided by, because you take 1 divided by 2. And here this is 1 minus 3/4 divided by 2, or 1 minus 3/8. You understand where I get the half and the 8? Yes, guys? You take this number, and divide it in 2. You take this number and divide by 2. This number is 3/4. And 3/4 divided by 2 is 3/8. So we simplify, I can multiply by 8 numerator denominator, and I get 4 over 5, or 80%. All right, now a slightly more difficult question, guys. Are you ready for it? No, hopefully interesting, okay? Here it is, guys. The crown prince is always the eldest male offspring in the royal family, which, by the way, is false. I can give you examples. Let's say Nicholas the First was not the oldest in the family when he was made Tsar. And the Decembrist revolution was supposedly about that, nominally was about it. So, but let's ignore that. Let's suppose that the crown prince is always the eldest male offspring in the royal family. If the crown prince is one of 3 siblings, what is the probability that he is the oldest child? You understand? So crown prince is the oldest male, but what's the probability he is the oldest child altogether? We know that he has 3 siblings. Sorry, not he is one of 3 siblings, so he has 2 siblings. Good. Interesting. So two people said 4/7. Very interesting. We shall see in a moment, guys. 1 or 2 more minutes. Well, let's see. Hopefully 1 more minute. Oh, another person says 4/7. Okay. Naturally, guys, well, why isn't it this? There are 3 possibilities. Either the crown prince is the youngest, or the middle, or the oldest child. So why is the answer not 1/3? Or maybe it is 1/3. Maybe you understand it so well that you are not. Yes, good. So, right, good. It's not equally likely, yes? So let's do it together, guys. Here is my Kafka protocol for the event F. And the event F is where you have 3 siblings. I'm gonna restrict to the situation where that happened, right? If there are 3 siblings altogether, then what we have is several possibilities, right? So we have this situation, guys, right? So maybe we have the crown prince is the oldest child, and then in other words, we have the oldest child is the boy, yes, and then we have here 2 and 2 possibilities, so we have altogether 4 possibilities where the oldest child is a male. Now here the oldest child is a female and the middle child is a male. So the middle child is the crown prince here. There are only 2 possibilities. And there is one last possibility, because we have a crown prince, right? Where the youngest child is the male, the first male that you have. You understand? So how did I break it? Oldest child is the male. Here I have oldest child is a female. And here and the middle child is a male. Then both the middle and oldest children are females, and the youngest is a male. Good. So altogether we have 4 plus 2 plus 1. We have 7 possibilities, as everyone who answered noticed. Congratulations, you're getting good at it. I hope you are using Kafka protocol or the same idea, at least mentally, right? We have 7 possibilities, which are clearly, we're assuming that the birth is completely random. So those 7 possibilities are equally likely. You understand? Assuming that each child, when birth is given, is equally likely to be male or female, then that implies that there are 7 possibilities. And out of those 7 possibilities, 4 of those possibilities correspond to the crown prince being the oldest. So it's 4/7. Everyone understands. Wow. Yes, guys. That's very impressive that you answered it, although it makes me somewhat sad, because when you don't have surprises, your life is blunt and boring. Right? Surprise is what keeps you alive. All right. Let's try a somewhat more extreme example. Or maybe less extreme example, okay? So, young Dolores sees a strange man, her mother's new tenant, looking at her through the living room window. Each of his first and last names is either Humbert or Quilty. She knows one of them is Humbert, What is the probability that his full name is Humbert Humbert if she is wearing one of 3 pairs of her favorite sunglasses, pair numbered 1? Hmm? You understood the question, guys, right? So the guy there, he has first and last name could be each of them, either Humbert or Quilty. What's the probability his name is Humbert Humbert if she is wearing her favorite sunglass pair? And he has Humbert Humbert as a name. So a lot of you. Oh, so somebody read the book. Well, congratulations, Anton, right? This is my way to test your literacy. Have you ever heard how Nabokov speaks English? It's pretty remarkable, right? And how was he speaking English this way? It's because in Russian nobility you were growing up speaking multiple languages. And that's why, especially literature that came out in the 19th century or later, somewhat later into the 20th century, imbues into itself everything from Europe and other countries because translations were incredible. So if you learn Russian, you'll have much better access to literature than you have with English and with other languages. The tip of the tongue taking a trip of 3 steps down the palate to top. Interesting. All right, guys. So let's look at the solution of this question. So let's consider the possibilities here and assume that I don't remember that quote, but Kunyan, nice, you read this too, I guess. That quote I don't remember. I read it already some time ago. So here we go. The restricted sample space is of what form? It's of the form Humbert Quilty 1, Quilty Humbert 1, Humbert Humbert 1. One of the names I said is Humbert. I think I said it in the statement, right? Otherwise, of course, it's right. So she knows one of the names is Humbert, right? I said that. She doesn't know if it's first or last name or what not, right? She knows one of them is Humbert. And so here are 3 possibilities. And so the probability, as you correctly pinpointed, many of you who answered, is 1/3. Yes? Assuming naturally that, assuming that that given that that Lolita is wearing her favorite glasses, that's not gonna influence. That's how do you say? So when she's wearing her glasses, the other 2 things can move as they like, right? It doesn't influence whether it's Quilty or Humbert. Now, here is another example, guys, and think about it carefully. So suppose your neighbor has 2 dogs. Each dog is either white or brown. Each of them has one of 3 favorite dishes. I mean, let's say the collection of dishes is the same, right, for both dogs. So there are 3 dishes, and each dog has one of those dishes as favorite. What is the probability that both dogs are brown if you see a brown dog eating its favorite dish in your neighbor's yard? So you have not seen those. You just heard that the dogs are either, each of them either white or brown from somebody else who speaks about them, right? And you never yet saw those dogs, and you know what are their, and you know that each of them has a favorite dish. So what happens if you see a dog eating its favorite dish in the yard? What's the probability that both dogs are brown? Okay. Are you clear with this question? Yeah, of course. So, right. So naturally assume all those things, right? So you assume that you can tell that it's the favorite dish of the dog. One of there are three dishes possibly available, maybe because you know the market. You go to that local market. Okay, Sarah says 1/2. Interesting. You understood my question, guys, right? So you know that before you observe, you know that each dog is either white or brown, and each dog, you know, has one of three dishes that it prefers. The collection of dishes that you have to select among is the same collection of three dishes. Now you see that here is this first time you see a dog. This dog is brown, and it's eating its favorite food. What's the probability both dogs are brown? Okay, Rwanda, interesting. Uh-huh. 5/11. Let's see what answer. Right, I'm still waiting for more of you guys, and we'll do it together. Interesting. Sure, they might share this favorite dish. Why not? Maybe each of them has the same favorite dish. Exactly, Alan. What does the dish matter? Does it matter or not? Now let's look at the solution. Are you ready? So a lot of you wrote 5 over 11 or 6 over 11. Interesting. So maybe you already think otherwise. Does the dish matter? You know, does it matter if you eat your favorite food? Do you become more brown or less brown? Doesn't seem like it, yes? So you think this information is not important for the dog, and you're correct. But you have to understand that your universe is not the dog. The dog is only a small part of the universe, okay? And when you study, let's say I told you there was this German quantum physicist who did not, who kind of was trying to explain that physically speaking, matter is not real. In other words, it's not, there's the probability waves or whatever he was speaking about. I think to the extent I could understand his flow of thoughts, what he is trying to say is if you study probability, you realize that, let's say, here is an eye, here is another eye. It's not a separate thing. It's just, it's artificially separated by your attention. But an eye and another eye are connected to the same face. Okay, so you and a traffic light and a grocery store are part of the same universe. There are features of the same universe that your mind simply singles out. Okay, so Alan, you are right away asking, let's say, what does, let's say, scratching my cheek, how would that influence anything on the eye? I'm not scratching the eye, but but it does influence the full probability. Good. So let's see how that might work, guys. Okay. So let's assume that the 3 possible dishes are Iams, kibbles, beets, and pedigree. So that's 1, 2, and 3. So those are the only thing available because you have seen what the neighbor, you know, you have been, for probability's sake, you were digging in the trash of the neighbor, and you know all the time you find those labels. Understand? So you know that his dogs definitely eat this particular food, one of them, all the time, and there is a favorite somehow, right? So now assume that each dog is equally likely to be either B brown or W white, and equally likely to have any of the 3 food choices as their first preference. So then the full sample space for the situation before I make any observations has 4 components, right? It's old dog and choice, young dog and choice. Do you agree? There is a distinction between the dogs, and I decide to make that distinction based on age. What is the color of the old dog and what choice of food? What's the color of the young dog and what's the choice of food? Clear? So what I have is, in this situation, for example, B1, B3, that means both dogs are brown. Old dog prefers brand number 1 and young dog prefers brand number 3. Now, what did I observe, guys? I mean, unless I'm very, very good at deciphering the difference between the dogs, which is the oldest, which is the youngest dog, I might have observed, without loss of generality, the old dog eating brand number 1, knowing that that's the favorite dish, right? And or I might have observed the young brown dog eating the dish. So I have observed either this or that. And guys, this is only a partial observation of the universe. You see, Alan, right? I mean, you think about one dog and its connection to the other. Their connection is that they're one part of the one universe, right? Here is one eye. Don't focus on the eye. That's not the object. Your object is the full universe, the full face. You understand? So my space is containing information about both dogs and their favorite dish, but I only made a partial observation of that universe. I cannot figure out what universe am I in. So either I am talking about universes that begin with B1 and 2 empty spaces, or end in B1 and have 2 empty spaces. Now, how many universes are there like this that correspond to my observation? So here, the number of possibilities is 2 possibilities for color, 3 possibilities for food, so it's 2 times 3. And here also 2 times 3, so it's 2 times 3 plus 2 times 3. It's 6 plus 6 or 12. And why do I subtract 1? Because I made an overcounting, right? When I counted universes of this type permits B1 to be the last, B and 1 to be the last two digits, the last two things that I write. Okay, and when I calculate this number of those universes, there is a B1 in the front. So that means that B1 was counted twice, and I subtract 1 to prevent overcounting. That's clear? B1 was counted twice. I subtract 1 to prevent overcounting, and what do I get? I get exactly 11. Now, I'm interested in the events where both dogs are brown. So the universes that I'm interested in have this form: B1, B, and not knowing what's the favorite food of the young dog, or not knowing the favorite food of the old dog. So how many universes are there like this? So here there are 3 universes, here another 3 universes, and where again we overcounted B1, right? So that's why I subtract 1 more time. So what do we get? 6 minus 1 is 5, divided by 12 minus 1, or divided by 11. So the number is 5 over 11. Now, so many people make errors in computing those probabilities. I already explained, hopefully, why, guys, right? Is that you focus, you just, you tend to think of the different aspects of the universe as separate, right? But here it's a sort of Buddhistic type of feeling that you are one with the universe, right? When people say one with the universe, whatever that might mean, that's probability, right? So the way the useful thinking for this subject is to think that the eye and the nose, I mean, what happens to the eye, you might say, does not influence to what happened to the nose. That's not completely true, because they are part of the whole, right? So so your observation, guys, the dog is not separate from the other dog. The dog that you're observing just gives you a partial view of that full feature universe that you're describing. So that means, guys, that every observation that you're making could potentially be very important, right? It might not have direct connection to the object you're studying, but it has a direct influence about the information in which universe you are. Okay, so some of you, what you do, for example, when you toss 2 fair coins, you think that if I ask you 2 fair coins tossed, first coin landed on heads, what's the probability both coins are heads, right? So what many of you do, you discard entirely the information on the first coin, right? You discard here two of them, you discard the information on the first coin. And you say, oh, the second coin is either heads or tails. That's not what I do. You understand? What I do is I say first coin is heads and the second is heads or tails. I don't discard it. I just, here is the difference. Okay, guys? So what do I truly imagine when I consider which information is important and which information isn't important, right? When I calculate probabilities, I calculate number of universes with probability with property E divided by total number of universes. Yes. And so what I do, guys, for instance, what it means, guys, is that you see, you can, of course, in proportion, much information is canceled out. You understand? Much of the information can be canceled out, so that's why I don't have to be specific about it, right? So some things that are in the numerator and in the denominator, when some information is not affecting probability because it equally cuts the number of total possibilities and the number of possibilities that I want. Okay, that's the situation. So here is an example. Let's see if we do it. If 2 fair dice are rolled, what is the probability that first die is a 6, and then B, the first die is a 6, given that the sum of the dice is 7? So it's a simple question, guys, but calculate. I think you would not have too much trouble there. Okay. All right. So you say A and B are the same. Okay, guys. So first here, the possible universes are just two dice. Okay, six possibilities, right? The desired outcomes that we have here. Look at it. The point of this question, guys, is that I don't throw away information. That's the point away, right? I actually put all this information. I imagine some of my document is filled, and what remains is to fill in what's left empty. So here, first die is a 6. So I don't ignore what happened on the first trial. I just put it to be 6, and the second could be anything it likes. So I consider this to be 6 over 36, which happens to be 1/6, guys. You see, because I could cancel it out. But 1 over 6 is the situation where I consider the second die by itself. It's a different universe where there is only one die, different collection of universes with only one die. You understand what I'm saying, guys? It's trivial for this example, but not always trivial, right? 6 over 36 is equal to 1 over 6. But on the left, I'm counting the universes that I have to consider in which 2 dice are rolled. On the right, I count the discarded in a universe where only 1 die is rolled, which many of you are just thinking of the right hand. You think, okay, I can discard this information as irrelevant and consider on the right. Okay, it happens that you get the same answer, but be careful, you are considering entirely different set of universes. Do you agree? In the second part, you're considering only 1 die, but in this problem, you're technically supposed to consider 2 dice. So I do not ignore when I have to consider 2 dice. I just imagine this information is filled in. Okay, I imagine this rather than just Y by itself. Clear? Now, for B, and the sum is 7, so of course here you consider this situation, guys, right? It's also 1 over 6, but here this is my sample space. If sum is 7, it's 6, 1, 5, 2, 4, 3. We know which of them is equally likely. So the reason it's 1 over 6 is because, well, I select 6, 1, right? And here I try to explain again, guys, I do not ignore one aspect. I consider the full document. Once I create a Kafka protocol, I consider the full situation, right? I just follow that protocol. All right, so here is multiplication rule. All right, guys, so one is really easy. 2 fair coins are tossed. What's the probability that first coin lands heads up? So again, what I try to say is many of you just ignore the false. So it's with many of you just consider that the sample space is just second coin heads, second coin tail, and you can calculate the probability that being 1/2. But strictly speaking, this is the sample space. It must contain information on both coins. You understand what I'm saying, guys? So be careful about throwing away information, right? You don't reduce your universes without, well, be very aware when you do that. Good? So strictly speaking, we see that the probability where the, what was the question? That first coin lands up heads. So first coin lands up heads means heads, heads, or heads, tails, which is 2 over 4, right? Which means that it has to be heads. Second part can do anything it likes. It just happens that we have 2 universes out of 4 total universes, and when I simplify, it happens to be 1/2. Good? So instead of discarding, guys, what can you do? In fact, assume that you know much more than you do. So the Kafka protocol, as I think of it, it's just a huge, almost infinite maybe not almost, but actually infinite string of boxes, many of those boxes are filled. It helps to know about the Day of Atonement, where, you know, like in the Jewish tradition, you are judged once a year in a book that's open and everything is known about you, right? Where you're written into the book of life or into the book of death. And so what I imagine is that this full information is written out, and only the unknowns. You see, when I throw the two pair of dice, guys. You see, for instance, when I said two pair of dice. Usually, you assume that the universe is only the number on one die and the number on the second die. What I assume is that I see my full universe. I know that I'm throwing them on a brown table. I know I'm throwing it in a room in Brooklyn, and every other aspect about every particle in the universe is known to me, except for the outcome on those two dice. You understand? So I imagine it's written everywhere else, and there are only two empty spaces that I need to fill in. That's the reduction. And because you know, whatever universes I can have, you see, once I take the ratio is completely determined by the two outcomes that are not filled. Because once I carry out the simplification, it comes down to only those factors. You see, because everything is determined, it's conditional. So how many universes where everything is given except for the outcome of the two dice? Only 36 universes. You understand? So it's not empty, it contains all the information, but the information on the dice. So that everything about my universe is determined, just not the outcome on the two dice. There are 36 universes now. Clear? Yes, I try to include to show you that, again, with any question, the way you think of probabilities, don't assume that useless information is useless. It might be just information that does not affect probability. The fact that Lolita was wearing sunglasses tells you more about the universe in which you're located, but it might not tell you more about the probability. The fact that a dog eats his favorite food, that does not make the dog brown, but it might tell you in which universe you're located, in which possible universes you're located. And it could be that there is a much bigger preference for brown dogs in the universes in which you're located. You understand? So some evidence might tell you that something is more likely to happen. Right? There is in general no preference, brown or white. The food does not influence brown or whiteness, but the food might be a marking, right? For instance, you see my chin, right? Like if all you could see is this chin, you might say, well, it's a very big evidence that maybe this person speaks Russian, right? And therefore that you might have a very brutal type of exam. So you see, it's not that that a chin affects the type of exam you have, but you might say, okay, this chin means Russian. Russians can be cruel, right? Right. That means that in universes where your teacher is having such a chin, there is more preference to difficult exams. But it's not that the chin caused the exam to be hard. Clear? Very simple. Yes, guys? You understand what I'm saying, right? It's like this, guys. If you're in a forest, it's more likely you will see a bear, right? But the forest is not producing the bears. It's right. It's more likely that maybe you should be worried about bears. So what happens here is an example, guys. It's a bit of a difficult question. 52 cards are dealt equally to 4 players: east, west, north, and south. If north and south have a total of 8 spades among them, what is the probability that east has 3 of the remaining 5 spades? That's an example of that thing that I hope you understood with my explanation. Okay. Dream. Okay. I'm waiting a little longer, guys. I hope you can come up with a solution. One six are interesting, right? I cannot see it as 1/6. Well, if it's 6 possibilities, first of all, I'm not sure what are the 6 possibilities. The possibilities must be equally likely, right? Just because there are 6 possibilities doesn't mean that they're equally likely. Make sure that you take that also into account. And why it's 6 possibilities, that also I don't understand. But I'm also in automatic mode. So. Yes, Andre. Good. All right, guys, in just a moment, I will reveal the answer. Yes, Andre's answer seems correct. All right, guys, we only have 3 minutes left to the class, and some already escaped. So here is the situation, guys. E is the event that East has 3 spades. Assume that the exact set of 26 cards that belong to East and West is known, and that 5 of these 26 cards are spades. Notice what I do, guys. I am assuming much more than I know. Right? What am I told? I'm told that West and North, I believe they have 8 spades, which means East and what else? East and who? East and South.
North and
No,
South,
so
obviously.
East and West, they have 5 spades among them, and I don't know anything about the cards that they have. And what I do here is I am actually assuming that I do. And you know why I do, but how am I able to do it, guys? I can imagine jumping through different universes, right? I mean, in each universe where it's true that 5 spades are shared among East and West, right? In each of those universes, the particular distribution of the cards is equally likely. Each particular distribution of the 5 spades is equally likely. Yes? Do you see that, guys? Right? It's like there is knowing the particular cards just means that I'm in a more definite collection of universes that will not influence the probability. I will explain below with simpler examples, hopefully. Here are just too many things to count, why it does not. You see, guys, we can, so to speak, simplify, cross away in denominator and numerator sort of factors that do influence which universe we have, but don't influence the probability. You see, if I count 2 universes out of 6, or if I count 1 universe out of 3, ratio is going to be the same. You understand? So some information cuts equally in the numerator and denominator, and therefore does not influence probability. Okay? If we're in a, you see, okay, good. So here, guys, I assume that I know exactly the 5 spades that belong to East West, and I know all the remaining cards. And so the distribution means that a person East must have 3 of the spades. So it's 5 choose 3, 21 choose 10, divided by 26 choose 13. You must have the remaining cards. Yes? That's how it must be distributed. I did not eliminate the other cards because it prevents me from calculating a nice ratio. It's also important. Why do we choose 10? Because altogether you have to have 13. East has to have 13 cards, 3 of which are spades. And the remaining cards are non-spades. You see, if I could, I would have eliminated all attention to the other cards, because I only care about spades. But the thing is, then it complicates calculation of you see, because you see, how are those cards to be distributed among 2 people? Exactly. Right? So? Well, you can consider it, guys. Think about it. Can you reduce it even further? Can you somehow solve this question without paying any attention to other cards? It seems a bit difficult because you have some sort of if one person gets a certain collection of cards. Well, think about it. Let's actually not say too much. Maybe you can be more efficient. Always try to see if you can be more efficient and can eliminate more unnecessary information for the calculation of probability. You understand? For the calculation of probability, you always have to imagine that you are observing the full, you're counting the universes. Otherwise, you can make a mistake. Good. So, well, guys, we will continue with more, hopefully, on and I talk about multiplication row and other things. We will hopefully continue on Wednesday. I'll let you know what happens, okay? So if you have some very brief questions, I can try answering them. I will probably not stay the full hour for office today.